electronic algebraic K-theory seminar. So today it's my pleasure to introduce Tony Feng, who will tell us about the Galois action on symplectic K-theory.
Okay, so thanks very much for giving me the opportunity to speak about this. And everything we're going to talk about is joint work with Soren, Galatius, and Akshay, Venkatesh. And I'm going to talk about a symplectic variant of the algebraic K-theory of the integers, which has the feature of coming equipped with a natural Galois action. So the talk is about describing that Galois action. And here's the plan. So first, I'm going to try to present some motivation and context by talking about some connections between K-theory and number theory. And then I'm going to talk about connections between arithmetic groups and algebraic geometry. And that will set the stage for talking about symplectic K-theory and why it has this natural Galois action. And then I'm going to formulate sort of the main results and touch on the ideas of the proofs. So let's begin with some classical motivation from number theory. There's a famous Riemann Zeta function defined as follows, and it's of great significance, for example, because it governs the distribution of the prime numbers. So it's a kind of fun game to calculate values of this Zeta function at integers. For example, you can calculate Zeta of 2, which is 1 plus 1 over 4 plus 1 over 9 plus etc. And it comes out to pi squared over 6. And in general, the values at positive integers will tend to be very quickly converging series of rational numbers, and so they tend to be irrational. What's a little bit surprising is that if you evaluate this at a negative integer, like let's say -1, then this is of course 1 plus 2 plus 3 plus etc. And that comes out to actually be -1 over 12. And you can keep going. The values at all negative integers are rational. And for example, just to give another sample, Zeta of -11, which of course is 1 plus 2 to the 11th plus 3 to the 11th, and so on, comes out to be, I think, 691 over 32,760. Okay, so of course, this is a slightly facetious equality. What I'm really saying here is that this function, which a priori is defined some like right half plane in the complex plane, admits a meromorphic continuation, which allows you to make sense at these points where the series, strictly speaking, doesn't converge. On the other hand, these values were calculated by Euler like many years before the advent of complex analysis. So it's kind of fun to play around and convince yourself that if it does make sense, it has to be equal to what I write down. And something which I want to emphasize here is that, as I said, there's sort of no reason to expect that the Zeta function, for example, takes rational values at integer inputs. Like it doesn't happen when the series converges. Nevertheless, somehow these numbers turned out miraculously to be rational numbers. And I guess the number theorist mantra is that if something which has no right to be rational somehow does turn out to be rational, then there's a good chance that it's counting something interesting. And so in this case, the Riemann Zeta function, these values at negative integers are counting the size of some algebraic K groups. For example, here's some true statement, which is a combination of a theorem of Mazur-Wiles and a theorem of Rost-Voevodsky. And it says that if I evaluate this Riemann Zeta function at negative odd integers, I'm going to get up to a sign in a power of 2, which is just 1 in this case, the ratio of sizes of algebraic K groups. In particular, these are both finite numbers. Maybe I should say I is bigger than 0 here. Okay, so for example, I guess K2 of Z is Z mod 2, K3 is Z mod 48. You can see that this checks out, and here you have K22 Z mod 691, and K of 23 is something blah blah blah. So, so I want to say a little bit more about where this equality comes from. So I think it's a combination of two different statements, each quite interesting. One is the statement, let's just talk about the numerator, that this K group, if I tensor with ZP, then it's isomorphic to a certain atal comalty-group. Okay, so as I say, this is a theorem of Rost-Voevodsky, and it's also it's a consequence of the Quillen-Lichtenbaum conjectures, which they proved. So on the other hand, this object, this étale cohomology group, is related to the zeta function by something called the Iwasawa main conjecture, which was proved by Mazur-Wiles. So these are two sort of separate but both very interesting stories. This one on the left is perhaps familiar to this audience, and it's meant to be analogous to the relationship between topological K-theory and singular cohomology. So I'm going to talk a little bit more about this relationship because maybe it's less familiar, and also it gives me an excuse to introduce certain characters in this story, which will have a recurring role later. So, for example, let's see. So this étale cohomology group, you can think of it as a singular cohomology group for a space, which is the étale homotopy type of this scheme here. So spec Z 1 over P. And what is there to say about this space? Well, what you should know is that it's an étale K pi 1. So then, kind of tautologically, that the pi is equal to, well, the étale fundamental group of this thing, and that has a natural interpretation in terms of Galois theory. It's some kind of Galois group. So in particular, it's some natural quotient of the absolute Galois group of Q, and more precisely, it's the kind of Galois group of the maximal covering space, which is ramified only over P. And so this thing here, this is meant to be interpreted as an étale sheaf on this thing, or a sheaf on this thing, or in other words, a local system, a representation of this Galois group. So which representation is it? ZP of 1 is a thing called the cyclotomic character, and it's the inverse limit of the p power roots of unity. So that's a group which is isomorphic to ZP, but the action of the Galois group is twisted. The action of the Galois group is through its action by permutation on roots of unity. And then ZP of I would be ZP of 1 tensor to the ith power, where if there's a negative number appearing, I interpret it as a dual. Okay.
I could just ask a question. Sorry, so in the statement about the connection to K theory, I guess I'm confused why it's H1 and not H2 that's contributing.
Oh,
to
sorry.
K4 minus.
So let's say, what do I want to say here? So I do want to say 2, but I also want to say that this is dual to some H1 something. Okay, so I probably should have put this on the other side, because I'm going to be explaining that there's a relationship between the zeta and the H1 of something. Thank you. Let's see. So what do I want to say here? So I want to just quickly draw a picture of this, of what this étale homotopy type looks like, because it's something which is maybe less weird than or less unfamiliar than one would think. So roughly speaking, the heuristic is that the étale homotopy type of rings of integers in global fields is like a 3-manifold, an open 3-manifold. So let's puncture a point somewhere. Whoops. And furthermore, the étale homotopy, so this is a picture of the étale homotopy type of spec Z 1 over P. So there's some punctures corresponding to Archimedean embendings, and then the étale homotopy type of spec FP is like a circle, and we're puncturing that out from here. So the boundary of this circle So there's some sort of like knot complement in a three manifold. And so that thing looks like a closed two manifold. So that's something which this red thing is like the étale homotopy type of spec QP. Okay, so I just wanted to draw this picture so that later when kind of we refer to such things again, there's some picture in mind. And in particular, because it's a three manifold, there's some sort of duality between H2 and H1. Although you have to mess around with these coefficients and boundary conditions a little bit. Okay, so what I want to say here is that H1 of this spec Z1 over P can be interpreted, because this is an étale K pi 1, this is some sort of group cohomology for this fundamental group. And so that can be interpreted as the space of extensions over this group between, well, two different representations. So we see here another interpretation of the group which shows up here, which is, it's related to some sort of space of extensions between two one-dimensional local systems. So in other words, this is some sort of space of two-dimensional Galois representations. And it's this interpretation, the interpretation of these cohomology groups as spaces of Galois representations, which most naturally makes contact with this right side of the story, with the zeta function. So, are there any questions? Okay, so something I wanted to emphasize was that, I mean, those of you who don't think about Galois representations, don't work with Galois representations, may not know like what to think about such a space. What does it look like? And I want to emphasize the point that it's something which is mysterious, even if you do work on them. Generally speaking, you don't expect to have some sort of very explicit or concrete or simple description of what such a thing looks like, or even when it's non-zero. And what one expects to be able to do is related to something else, which is also mysterious. And so this is the subject of the Langlands correspondence. So it provides some sort of interpretation. Okay, so the connection between this sort of x1, oops. So I want to say x2, which is x1 of something, again, comes morally from the Langlands correspondence, which relates automorphic forms and Galois representations. Okay, so for example, the kind of thing we're saying is when a certain L value is 0 mod P, then there exists a non-trivial extension. And here's a sort of example of this, how this kind of statement is proved in practice. So this style of argument was given by Rivet. And it says that we can interpret the value of the zeta function as a Fourier coefficient of some automorphic form on GL2. And now, by the Langlands correspondence, you can extract from an automorphic form a Galois representation, a two-dimensional Galois representation. And then you use the fact that this zeta value is 0 mod P to argue that you can actually make this two-dimensional Galois representation a non-trivial extension. So on a priori grounds, it would be reducible, but you want to show that somehow it's a non-trivial extension. Okay, so this is the kind of argument which one makes in general. Mazur-Wiles gave a sort of enormously enhanced version of this to prove this Iwasawa main conjecture. Okay, so I want to sort of focus a little bit more on this mechanism, because this is somehow at the heart of this talk. The mechanism which allows you to extract Galois representations from automorphic forms. In fact, so it's true in general that anytime you have a congruent subgroup of GL2Z, meaning a subgroup which is finite index defined by congruence conditions, then there's a natural Galois action on that group cohomology. And for our purposes, we could in fact interpret automorphic form to mean a class in this group cohomology. Then this red arrow, which extracts the Galois representation, just means you take the thing and you look at sort of its Galois translates and look at the representation that generates. So the existence of this action is providing this kind of mechanism in this situation. And I'll review shortly like why this thing exists, why this Galois action exists. But I just wanted to say it's true in a lot more generality that when you have arithmetic groups, for example, gamma's sp2n of the integers, this is the example which is the most important one for this talk, but also if you put in orthogonal group, or if you took like a unitary group and you could even allow some kind of rings of integers in a number field, you would still get Galois actions on group cohomology. And roughly speaking, the philosophy, the Langlands philosophy is that that all Galois representations with appropriate adjectives can be accounted for in the cohomology of arithmetic groups. So this is some sort of notion of automorphic form. But I would caution that one shouldn't try to extrapolate more than I've said. So it's the class of arithmetic groups for which you have this Galois action, like this kind of Galois action on group cohomology directly, is pretty sparse. It was classified by Deling. And when I say account for, I mean some more general procedure, which certainly hasn't been discovered in most cases. And once one tries to make precise what the adjectives should be, it's also very complicated. But roughly speaking, this is the philosophy. Okay, so to summarize, what I've said is that there's surprising connections between algebraic K-theory and number theory, and one can see them as being mediated by this theme of Galois representations and their relation to the cohomology of arithmetic groups, which is something predicted by Langlands. So are there any questions before I move on? Okay, so if not, I've checked off my first bullet point, and now I'm going to talk about the connections between arithmetic groups and algebraic geometry, which is what explains why this Galois action exists. So that comes from discussion of moduli spaces of abelian varieties. So what I'm going to do is explain for the arithmetic group gamma being sp2gz, the connection between its group cohomology and Galois representations, in particular why Galois acts on its group cohomology. This will turn out to come from the fact that there's a very special model of this classifying space, sp2gz, a model which is an object of arithmetic geometry. And informally, the statement is that this classifying space is the étale homotopy type of the moduli space of principally polarized abelian varieties. So this is something which I will explain. Okay, so first of all, maybe what is an abelian variety? Well, it's a type of a variety. So maybe we should think first to the situation of the complex numbers, which is the most intuitive one. So an abelian variety has an underlying complex manifold, which is a complex torus. So abelian variety of dimension G, well, its underlying manifold is then of the form C to the G modulo some lattice, abstractly Z to the 2G. And the statement that it's an abelian variety says that it actually comes from some algebraic thing. So you can think of that as you need to specify a polarization on a complex torus in order to see that it comes from an abelian variety. Concretely, a polarization is a symplectic pairing on this lattice lambda, which has appropriate positivity conditions. Or you can think of it as trying to describe kind of in terms of cohomology, like what is the Chern class of an ample line bundle, which gives the A its algebraic structure. So I'll explain what this means a little shorter on a little later when I want to make that precise. So what we want to do is contemplate the moduli space of such data of abelian varieties over the complex numbers and try to figure out what it looks like. So what we've seen is that I have to give the data of like lambda symplectic lattice inside a complex vector space. So first of all, lambda, this word principal means that it's going to be a perfect symplectic lattice integrally, and there's only one such thing of isomorphism. It's necessarily free over rank 2G on generators E1 through EG, F1 through FG, with pairing matrix. The standard one for a symplectic form. So it's like, let's say this. So the lattice, abstractly the lattice, the symplectic lattice has to look like this. And then we can start asking ourselves, like, what's the moduli of the ways to embed this into a G-dimensional complex vector space? So it turns out if you want this to work, then you have two different bases. This F vectors will form a basis of this G-dimensional complex vector space, and so will the E vectors. So they're related by a unique G by G matrix. And the condition that your lattice, that the symplectic form is a polarization, you can unwind it to see that what it means is that this matrix had better be symmetric, and its imaginary part, which is some symmetric matrix over the real numbers, has to be a positive definite. Okay, and so this completely describes like the data required to construct the abelian variety. And so we're motivated to define H sub G to be the space of G by G matrices satisfying these conditions. They're symmetric and their imaginary parts are positive definite. And so this is something called Zegal's upper half space. So in particular, when G is 1, this is something probably familiar. It's just inside the complex plane, you take the usual upper half space. Okay, so what have we said so far? So what we've said amounts to the following. The space of complex abelian varieties plus the data of a symplectic basis for the lattice, which defines it, which can be recovered from A as its first homology group, is equivalent to this this Zegal upper half space H sub G. Now, I didn't want to actually carry around this data of the symplectic basis. I want to mod that out, and so that I just take the quotient by the action of sp2gz. So there's some sp2gz torsor, and then I get a description of the moduli space of principally polarized G-dimensional abelian varieties over the complex numbers as the quotient of the Zegal upper half space by sp2gz. Now, let me caution here that I'm taking this quotient in a stack sense in order to make it. Okay, so this is a stack quotient. So strictly speaking, this group doesn't act freely on this Zegal upper half space, but its stabilizers are finite. So as long as I'm willing to call the quotient an orbifold, then this really is an sp2g torsor. Also, a very important feature of this Zegal upper half space H sub G is that it's contractible. So of course, in the usual G equals 1 case, you can see this visibly. The upper half space is contractible, and you might have also seen these pictures. So this is a fundamental domain for this action that we're pushing out by for the SL2Z action. And that's why G is 1, and abelian variety is called an elliptic curve. And so you might have seen pictures of this thing as being like the moduli space of elliptic curves. So anyway, because we take the free quotient of a contractible space by the action of a discrete group, then this quotient we get is therefore a model for the classifying space, BSP2GZ. On the other hand, this thing, which I'm just going to define to be AG of C, this is a priori some sort of complex variety, like complex stack, but it turns out that there's an actual algebraic stack over the complex numbers. Maybe I'll call that AG sub C, for which this is the actual complex points. So if you take C points, you'll get this thing that we just described. And it's true in general that if you have a thing like some sort of variety or stack over the complex numbers, and then you take its actual complex points, getting some sort of complex analytic stack, then this thing would be a model for the étale homotopy type of this, at least after P completion. So let's collect these coincidences which we have observed. So there's a few key coincidences here. One is that this quotient is a model for the homotopy type BSP2GZ, and that would imply that the group cohomology of the symplectic group is isomorphic to the singular cohomology of this classifying space. So isomorphic to the singular cohomology of this quotient. On the other hand, yeah, I kind of identified this with the singular cohomology of AG of C. And my statement here is that because these are the complex points of an underlying algebraic thingy, that this is identified with the étale cohomology of that algebraic thingy. Okay, so at this stage, it's before this we could have put any coefficients, but now we had better put some sort of p-complete coefficients. Maybe to emphasize this, I'll put ZP here. And yeah, okay. So we have a sort of fortunate coincidence that the group cohomology of the symplectic group actually has this interpretation as an étale cohomology group of a algebraic stack. And this coincidence reveals sort of extra structure on this thing. Okay, so
sorry, before you go on, there was a question from Kyle in the chat. Does the invertibility of tau follow from tau being its transpose and positive imaginary part?
The invertibility of tau. I think so, because I think, yeah, the description. I think it does, next, but I mean, it is invertible. That's definitely true. Okay, so as I say, this coincidence reveals extra structure here, and in particular, I'm going to use that to explain where the Galois action comes from. So the point is that there's a purely algebraic definition of the notion of a principally polarized abelian variety over any base scheme. You would say like a proper variety connected dimension G, something like that. And so that implies that there is a notion of an algebraic stack, which makes sense over any AG, which makes sense over any base scheme. It'll classify sort of flat families of principally polarized abelian varieties of dimension G. And if you take the complex points, you'll get the thing that we had just discussed. You'll get this upper half space mod SB2GZ. So that kind of justifies this notation we had been using. And so in particular, the incarnation of this stack over the complex numbers, the AG sub C, is seen as coming from some deeper base, some sort of more fundamental structure, a thing which makes sense over the rational numbers by a base change from the rational numbers to the complex numbers. And because it's presented in this way, it has an obvious action on automorphisms of this second factor. Okay, so this algebraic stack has a natural action of the automorphism of the complex numbers. On cohomology, you can see that this action factors over the Galois group. Okay, so this reveals extra symmetries because this thing itself has an algebraic action of this automorphism group of the complex numbers, and it's equal to this other thing, then you see that structure on the left-hand side as well. Okay, so the upshot is you have a Galois action on the group cohomology of the symplectic group via this chain of identifications and ultimately coming from an algebraic action on this thing. Now, a couple of comments. So the action of this on this thing doesn't come from an action on the actual like homotopy type, on the actual space. Like really, this came from the fact that this acted on AG of C, which was then identified with this thing. But that action is far from continuous. I mean, it's like an automorphism of the complex numbers induces an action on the complex numbers, but an incredibly discontinuous one. So that's why it was a little bit subtle to see action in the first place. However, there's a better statement one can make, which is that if you can p-complete this classifying space, then the action, well, it is some sort of continuous action, because this classifying space p-completed is interpreted as an étale homotopy type. So it's interpreted as the étale homotopy type of the moduli space of abelian varieties over complex numbers. And in particular, this étale homotopy theory is a functorial construction from a variety or a stack to its étale homotopy type. So an algebraic action will become a continuous action. So the fact that we said something more refined, that we are able to get an action on an actual space, it will be important later. Okay, so to summarize, what we've seen is that there's a Galois action on the group cohomology of the symplectic group, and it arose from the fact that the classifying space p completed here is the p-adic étale homotopy type of the moduli space of abelian varieties over the complex numbers, but then that could be interpreted as the base change from the rational numbers. So I've said all I intended to say about this connection between arithmetic groups and algebraic geometry. So are there any questions before I move on?
Sorry, so could you summarize again what's the main point of this second part?
The main point of the second part was to explain that this action comes about from this connection between the symplectic group and the moduli space of abelian varieties. Mm-hmm. And also to sort of drill in this idea that the action exists on some kind of space as well. It's actually just the classifying space of the symplectic group after you p-complete.
Okay, sorry. Then could you repeat again? You just said that the action does not come from the action on BSP. Can you show above a little bit?
If you don't p-complete it, you won't get an action. And one way to see that is that if you don't put in p-adic coefficients, you won't get an action.
Oh, that's cool. Okay, sorry. Thank you.
No problem. Thank you for the question.
So sorry, you're saying that you know that there is no action on the rational cohomology?
Oh, okay. So I mean, there is there's no action which induces this action. You could define something silly like a trivial action, but yeah, and that's basically just because the Galois group can't act in an interesting way on these like discrete groups. So the profinite topology on the Galois group is not compatible with what you would see if you didn't put the CP.
I see.
Sorry, maybe I can ask a question. So, I mean, is this like p completion or profinite completion? Does it do something nice on pi 1? And do you also get like an outer action on?
Yes, I think it's right that the p completion induces the p completion on pi 1. Definitely not true for the higher homotopy groups, but on pi 1, yes.
Oh,
sorry, I guess I mean, like, is the pi 1 of, I mean, is it going to be something like the symplectic group of Z hat or something, or is it sort of more?
I think that for SP2DZ, if you p complete it, you'll just get like 0 or something.
I mean, I think it will produce something that's not a one type, this p completion.
The p completion is definitely not a k pi 1 anymore. Yeah.
Thanks.
I don't think you can just.
But I think, yeah, the property of this group, if you p complete it, then the fundamental group actually becomes extremely small, maybe trivial.
I think you need something about nilpotent in the group, or I'm not sure.
But yeah, I definitely want to emphasize that this thing is not a k pi 1. Okay, so what I'm planning to do next is use what we've learned here to tell you about symplectic K theory and why it has a Galois action. So first, maybe I'd like to frame it in analogy with the usual construction of algebraic K theory. So to do this, to construct algebraic K theory, you consider the group void of finite projective R modules. If you wanted to find K0, which I guess maybe Grothendieck first wrote this down, but it's certainly a very old idea, that you take isomorphism classes within this category. That's a priori set, but it's a monoid under the direct sum operation. So direct sum induces a monoid structure on isomorphism classes. Then you group complete, and there's your K0. And to define Ki, you perform a more refined version of this construction, where you, instead of crushing things down to isomorphism classes, you take the classifying space of the category. In other words, the nerve of the geometric realization of the nerve. And you'll get, for similar reasons, a monoid, but now in spaces. And then you group complete, and you get a group-like space. And then you take the higher homotopy groups. Those are the higher K-theory groups. So to define the symplectic K-theory, we're just going to do a very similar thing where we replace the category of finite projective R modules by the category of finite projective R modules equipped with a symplectic structure, or in other words, symplectic R modules. And then you say the same magic words to get the symplectic K-theory.
So sorry, since we are over Z here, can you ask you exactly what you mean with a symplectic structure? Because
what I mean is the module, I don't know, let's call it P. You want to give it an isomorphism with its dual, such that like.
Okay, so you don't mean, for example, that BXX you don't mean it's alternating, for example, or any others. Just a non-degenerate antisymmetric linear form.
Oh, you're talking about like at 2, right? That's what you're.
Yeah, because we're over Z, right? So you have to be careful about.
Yeah. This does present an issue. I honestly don't remember how we define it in the paper, but it'll turn out that because we're going to work at an odd prime, it doesn't matter. But you're right, there is an issue here.
Thank you.
That's what I was going to say. So I think of algebraic K-theory is related to the algebraic group GLN, and in an analogous way, the symplectic K-theory is related to the group SP2N or SP2G. So this is the definition. Now, there are some sort of more concrete relationships between K-theory and more elementary things. For example, the relationship between K-theory, ordinary K-theory, and stable homology. And it comes from Quillen's plus construction, that this can also be presented as the homotopy groups of something else. The plus construction applied to the infinite general linear group. And so there's like a Hurewicz map from this guy to the homology of this fellow, which then is the same as the thing without the plus. So that's why it's called stable homology, the homology of this infinite classifying space. And a similar statement is true about the symplectic thing. It's the homotopy groups of the plus construction applied to the infinite symplectic group over the integers. And in particular, there will be a map from this thing to the stable homology, the homology of this guy, which is identified with the homology of the group without the plus. Okay, so as I say, this gives some relationship between K-theory and stable homology, maybe a more elementary notion. And a little historical remark is that for 2 years, the draft of the paper was called the Galois action on stable cohomology of AG. And sort of we're trying to formulate the results in terms of cohomology. K-theory still played a role, which maybe I'll say later, but yeah, it was trying to be about homology. But crucially, the results were only sort of valid when P was large with respect to the homological degree. As soon as like the homological degree becomes, it was something like P bigger than 2i. As soon as I got a little bit too large, then the proof broke down in like many places, all at the same point. And we ultimately realized that passing from stable cohomology to stable homotopy theory, stable homotopy groups, allowed to remove this restriction. It sort of restored the good stuff going on. And so I'll try to highlight a little later on, like a couple points where this kind of thing happens, that stuff goes haywire in homology, but kind of behaves well on homotopy theory. Okay, so one of the main, maybe the main reason we consider the symplectic variant is because it comes with a natural Galois action. So I'll state this as a theorem, I guess, that there's a sort of natural automorphisms of C action on these P-completed symplectic K-theory groups. And yeah, probably should have stated here, but it factors through the quotient to the Galois group, absolute Galois group of Q. And sort of the fundamental point to see this action is the same as it was on homology. So to spell it out, the symplectic K-theory was defined in terms of this category, the category of symplectic modules over the integers. And so we took its classifying space, and this is equal to the disjoint union over classifying spaces of these symplectic groups. Now, if you p-complete things, so you p-complete this thing, and the key point was we had seen that this admits a kind of algebraic interpretation as the homotopy type of AG over the complex numbers, or really to see the action, we should think of this as AG over the rational numbers, base change to the complex numbers. The p-adic étal homotopy type. And here there's a kind of evident action of the automorphisms of the complex numbers. And so then there's an action on this thing, and then you produce K-theory by some functorial construction from this thing. So there's an action on the K-theory. So let me just kind of leave the sketch at that. But if you want more details, there's a sort of painfully long appendix in the archived version of the paper, which explains this, I think, to very large resolution of detail. Okay, so the upshot of this discussion was that there's a symplectic version of K-theory, which is defined like the usual algebraic K-theory, but replacing the category of R modules with the category of symplectic R modules. And then in the case where R is the integers, there was a natural Galois action on that, at least on the p-complete K-theory. Which, yeah, I'll just say, but by known finiteness results is the same as just tensoring the symplectic K-theory with ZP. Okay, so I've now checked off this third bullet point. Before I move on to talk about the results, are there any questions?
For what you just did, were you supposing P to be odd, or does that not matter yet?
So it's true when P is not odd, but I guess my definition was slightly ambiguous. So I will certainly be assuming P is odd whenever I state an actual. So I don't think I need it here, but when I sort of say what the Galois action is, I will be assuming P is odd. So the point is that, like, if you also work with something kind of finite index in the symplectic group, then the action will still exist. So the issue of what happens at 2 doesn't matter too much.
Is there an analog of this for standard K-theory instead of symplectic? And if so, what would the moduli problem be?
A good question. So this will come up kind of later, but no, there is not an analog. So if you look at these classifying spaces of BGL and Z, I mean, there's something analogous, which is it's a locally symmetric space for GLN. So this is the analog of this kind of HG mod SB2G presentation. But this thing here then turns out not to have an algebraic avatar. In fact, sometimes it's like odd real dimensions. So it definitely can't come from an algebraic variety over the complex numbers. So yeah, for the usual algebraic K-theory, exactly because we don't have an algebraic interpretation of this fellow, we don't have a natural Galois action on it.
And what about Hermitian K-theory, since we're asking? So B, O, G, or 2G, I don't know.
Yeah, so this is a delicate question. So generally speaking, like if you put in a totally real field, you can expect, and you can sort of expect it to exist, at least sometimes. If it's not totally real, then you cannot expect it. So definitely an interesting question, which, as I say, like has a delicate answer. So basically, the question is when are these classifying spaces like B gamma Shimura varieties? And the answer to this was basically classified by Abelian. But there's certainly other examples other than the symplectic group where it happens, but also certainly not all examples. In some sense, the examples are sparse in the space of all possibilities.
There are a couple of questions in the chat as well.
UN. So for example, UN, you have to be a little more specific about which field we're talking about, but it is okay, except then there isn't a K-theory stabilization unless you also put it like a signature condition that is kind of stable under direct sums. So like usually people work with UN1 Schumer varieties. This is not okay. UNN is okay. And then there was a question about, is there some action that one gets on B Z mod 2? So I think maybe I'll touch on this later, but yeah, I guess this is a, depending on how you interpret the Z mod 2, like you can maybe make an action or not, but I think this sort of map that you're talking about will hopefully be, it's sort of Galois theoretic significance will be touched on later. Okay, great. So thanks for the questions. Let me say a little bit now about our description of the Galois action that we see. And so, yeah, our general question is like, what is the Galois action on this symplectic K-theory group? However, before we answer that, maybe we need to answer like, what does this thing look like just even as a group without considering its Galois action? So there are some obvious structure present. For example, you can include the general linear group into the symplectic group of a larger dimension by embedding it as a levy. For example, if you take any n by n invertible matrix, then you make this thing, this will be a symplectic group. And so that induces a map from the usual K-theory to the symplectic one. And it's certainly clear that a symplectic matrix can be regarded as just a matrix. So that induces a map from the symplectic K-theory to the usual algebraic K-theory. And so we're going to try to relate the symplectic K-theory to the usual one, to the ordinary algebraic K-theory. So there's a theorem of Karoubi that if P is odd, then in degree 4i minus 2, the symplectic K-theory is of this form. It's the direct sum of the usual algebraic K-theory plus CP. And the map, like you can take the maps to be the one that I just explained. Like this map is, we're going to want to consider this map, and this map is this map. And as I understand it, a recent series of papers by 9 authors clarifies what happens when P is 2, for example. But the theorems that I'm going to state are only for P being odd. And I did also want to remark that we were definitely making crucial use of this theorem even when we were trying to write this paper for stable cohomology. Basically, it was the K-theory which provided the group theoretic control even on cohomology. And that came from this theorem, and something which I'm given to understand is that one should think of this theorem, so I haven't really done justice maybe the way I've written it, but one should think of this as a periodicity statement. It says really what's going on is that kind of the difference between these two is a thing which one proves to be periodic. So this kind of periodicity phenomena for K-theory is going on here. And that's something which is hard to see purely in homology. Okay, so continuing on. So we know something about the underlying group. Now we're going to try to say something about Galois actions. So we actually produce an explicit Galois equivariant map from the K-theory to ZP, but then it needs to be understood with this cyclotomic character that I had mentioned before. So this is this limit of mu p to the n, tensor to I minus 1. Okay, and so this map, the key point is this map is Galois equivariant. When I put this Galois module on, Galois structure on the target, the natural one on the domain. And the map is induced by mapping K-theory of Z to K-theory of R, symplectic K-theory, after all it is functorial, and then observing that, that this is sort of the same as this connective K-theory in the usual sense, because ultimately that the symplectic group of R is homotopy equivalent to the unitary subgroup. So in general, a Lie group is homotopy equivalent to its maximal compact subgroup. And one knows the homotopy groups of this thing are this thing, even in a Galois equivariant sense. This is like maybe part of about periodicity. So just to remark that this name, Hodge map, comes from a relationship between this map and Hodge cohomology. So when again, back when the paper was written in terms of cohomology, it's constructed in a slightly different way. Namely, we took the Hodge bundle over the moduli space of abelian varieties and took its Chern classes. So to explain this, so we're looking for a certain vector bundle, omega g over ag. Well, that should assign to every point of the base a vector space, and the point of the space, the base, is an abelian variety, and the vector space which it assigns is the Hodge cohomology. So H0 A omega A, or concretely, that's really just the same as the cotangent space of A as a vector space. So anyway, given a vector bundle, you can make Chern classes. Those will live in cohomology. But kind of the rub here is that it's in rational cohomology a priori, because turns out we want to take this sort of 1 over 2i minus 1 factorial thingy normalization. But anyway, given cohomology classes, you can certainly get maps out of homology classes. By capping with them, and then you have this like Hurevich map from K4i minus 2 to here. And oops, sorry. Yeah, so I said that this was QP. When I is small relative to P, of course, you're dividing by a unit, so you can kind of, it's even an integral thing. And then, yeah, this composite map is the Hodge map. Then when I is big relative to P, this Chern class is no longer integral. This thing is no longer integral. So you're kind of dividing by 0. But on the other hand, the image of this and this is also becomes zeros. So like maybe you can make sense of it. It's 0 over 0. Ultimately, it was just much cleaner to work with stable homotopy theory, and it has this very like concise description. So this is another point.
With respect to the description on the previous page, like what happens when you restrict the Hodge map to each of the factors?
So yeah, so we prove by hand that this is surjection. We don't say a priori that this map is the same as this map. That being said, once one knows that this is a surjection, then the kernel must be this thing. So you could take this map to be the Hodge map.
Oh, okay. Thanks.
Okay, so let's just collect what we know, what we think is true so far. So Karoubi tells us that symplectic K theory is a certain direct sum like this as underlying groups. Then we constructed some Galois equivariate map like this. So that kind of describes what's going on Galois theoretically on this factor. We also guess, for the reasons I mentioned earlier, that the Galois action is trivial on here, just because like, what else would it be? We don't know how to define anything else that's natural. And finally, if you're familiar with arithmetic geometry, you would expect that the action should be unramified everywhere except over P. So you expect the action factors through this kind of fundamental group, which I had written down earlier. So it almost seems like we've guessed what it is everywhere, and it's kind of trivial. It's just like on here, it's a cyclotomic character. On here, it's trivial, but there's still room for a little bit of stuff. There's room for a non-trivial extension. So our representation, Galois representation, looks like this. There's a quotient, which is this CP 2i minus 1, and then a sub where it acts trivially, and then a 0 here, but here there could be something non-trivial. And the statement of the theorem, somewhat informally, is that it is the action is as rich as possible subject to these constraints above. In particular, the extension is as non-trivial as possible. So, for example, if there exists a non-trivial Galois extension of this form, then the one that you see in symplectic K theory is non-trivial. So that's the kind of informal version. To make this more precise, we need to try and codify what it means for an extension to be as non-trivial as possible. And the way we do that is by thinking about sort of a category of possible extensions. So the setup is like we contemplate a profinite group gamma. In our minds, this is pi1 of z1 over p. And then some map from H. This is maybe a little bit harder to motivate, but it'll end up being spec QP, pi1 of QP in the situation of interest. and then a gamma module M, which will be ZP 2i minus 1 in the example of interest. And we contemplate the category of all possible extensions of M by as a gamma module by a trivial kernel. So we make a category C gamma HM, whose objects are extensions of gamma modules. Let's call these the total space of the extension U, so it has a surjection to M, and we demand that the kernel has a trivial gamma action. And then something which is less clear a priori that you should put in there, but we ask for a splitting of the restriction of this extension to this group H. So this definition is modeled on what we see or what we expect to see on symplectic K-theory. And a little short lemma will show that this kind of category will always have an initial object. And so this is one of the reasons we put in a splitting, is to rigidify it enough so that this is true. But okay, so
there's just a question from Ellen, whether the gamma action on the kernel is trivial was not.
Very good question. So so as I say, this was just a guess of what should be true. So it'll end up being proved that it is trivial, but it is something that that gets proved at the same time as everything in some sense. Like we don't prove it a priori and then put it in this category and then show that it is the initial object. So we don't know it's trivial. It'll end up being proved at the same time as like everything. So this is, if you will, like a model of what should be going on. And similarly, like we don't know that this extension has a splitting when we restrict it to this thing a priori. And so that gets proved at the same time as everything else. Everything gets sort of proved at once. Okay, but just to emphasize, the example we have in mind is where gamma is the fundamental group of the integers punctured at P. H1 is the fundamental group of the p-adic numbers, mapping to gamma induced by the obvious map of schemes. And then M will be this cyclotomic character power. And so this category has a universal object, unit 2i minus 1. And the more formal version of the theorem, or the precise statement of the theorem, is that that we can make sense of the symplectic K-theory in this category. In particular, the map from the symplectic K-theory to this M is going to be taken to be the Hodge map. And then as an object of this category, it is the universal object, the initial object. But yeah, as I say, like we don't sort of a priori put this in this category by seeing that the kernel has trivial action and that there is a splitting. It's sort of everything gets proved at once. And it's certainly something where I think there's room for kind of more conceptual explanations for why some of this like structure exists, like why the kernel has trivial action. Okay, so I see I'm sort of out of time. So let me just maybe mention. So if you don't work in a certain subject, this statement maybe looks a little bit contrived. So I just want to compare it to the kind of statements that one does see a lot in that subject. So as I say, you could all think of this as connected to Langlands philosophy. And there's like a long tradition of papers, many papers proving so-called R equals T theorems, starting with the seminal work of Taylor-Wiles. And what such theorems say is that when you take the group cohomology of an arithmetic group and you complete it at some cuspidal Hecke eigensystem, well, it has a Galois action in the cases where this kind of thing is proved. And one proves that it is the kind of universal Galois representation satisfying sort of obvious constraints that it needs to, and even some non-obvious constraints. And in these cases, this thing always turns out to be irreducible. And so you can think of our theorem as proving some sort of statement of this nature, except it's instead of being about cohomology, it's about the K-theory. And we show that it carries some sort of universal Galois representation satisfying all the visible constraints. But in our case, that also forces the thing to be reducible. Okay, and so let me actually just stop here and thank you for your attention.
Okay, let's thank Tony for a very nice talk. Are there any questions?
I have a question sort of more on the number theory side. But in this might follow from what you just said, but if you sort of go back to Ribot's method or maybe the Mazur-Wiles method, and let's say you have some class in K theory and you're proving about it something using a specific modular form, like does that modular form then have some class in the cohomology of a modular curve, which then can be related to the sort of K theory class in your setup that gives the extension?
So yeah, I guess one can look at it as like there's a certain, so oops, let me see. So I think the question means something like this. I had explained that the K theory of Z, I don't know, let's call it 4i minus 2, was some sort of dual group to some sort of x1. And now the question is, well, maybe I'm going to say something and let's see if it answers the question. So when you have a universal extension, you typically expect it to look like a dual to x1. Then yeah, the thing that you're extending. So the symplectic K theory looks like this. Or maybe I should really say like you would expect the universal extension to look like this thing, because the universal extension, it has an extension class, and that extension class is like x1 with coefficients in something. And that something, if it's universal, it should be like the dual to x1. So the universal thing looks like this, and the K theory, the symplectic K theory looks like this. So yeah, I guess what I'm saying is symplectic K theory looks like this, and the kernel looks like this. And so when you identify them, you do see that like somehow the extension class, oops, sorry.
Meant to write no SP.
Yeah, you do see that like the K theory class is related, is the extension class in such sense.
You get like the sort of relation between K theory and motivic cohomology from what the Chern class map.
Chern class map from what to what?
Like well, you have the Chern class map from algebraic K theory to a tall cohomology.
Yeah.
And so the point is that this is that map.
This thing
suitably
is that map. Yes. This map is like the Soule map.
Right. My question was a little further, but I don't want to go down too much of this rabbit hole if other people have questions. I guess I could say more.
Sure.
I mean, my question is sort of then, but then if you remember the fact that symplectic K theory is somehow related to moduli spaces of principally polarized abelian varieties, and modular forms show up, well, let's just say classical modular forms show up with modular curves, then sort of, I mean, maybe one question would be, could you relate it to the kinds of maps that Romeo Sharifi has, where he actually has some map between some sort of homology of some modular curve and one of those Galois, one of those étale cohomology groups.
Yeah, so I don't think our thing is related like directly. I mean, philosophically certainly, but certainly like the H1 of the modular curve is not in the stable range where it's actually touched by the K theory. But
so you can't think of a way to relate the H1 of the modular curve to something in this symplectic K theory.
Yeah, so I don't think that the part that the symplectic K theory relates to is a sort of stable range where you don't see that kind of thing. So I don't think that it. I mean, it maps to H1 AG for G large, but H1 of SP2, it doesn't really. Yeah, it's really stable.
Well, there should be a map. It just might be trivial.
So what is the question? The question is this map, or is some map in this picture like the same map as Ramyar, or somehow closely related to it?
Yeah, I'm not being. It's a little vague. I'd have to sort of look at it a little more carefully to formulate it better. So I could ask you later, but yeah, basically something like that.
I think the answer is no, but yeah, I guess it depends on how liberal one wants to be when in the word relation. But I think it's like philosophically related, but not literally related.
I have a question, if I may. So you did this for the symplectic K-theory of Z, right? Because you found a nice presentation for SP2GZ, well, BSP2GZ. What about other rings of integers? Is the
So
I mean, can you find like a functorial model for BSP and O?
So when you BSP2GOF, where F is totally real, is a good thing. Whoops. Like this thing would be moduli of abelian varieties of dimension something depending on F with an action of OF. Like, so this is something where I think very similar statements should be true. I think at some point we sort of wrote down, well, without thinking about how to prove it, like what the statement should be. And yeah, when it's totally real, there exists such a thing. When it's not totally real, there isn't.
Why do you need totally real for this? Sorry, I cannot see where the condition plays a role here. That's why.
It's connected to the question of when is B gamma, when does B gamma, or maybe I should say it this way.
Okay,
So,
maybe I should ask a more concrete question. You can still define that moduli space of abelian variety with an action of OF for any F, right? I mean, that you're allowed.
yeah.
What goes wrong? I mean, you get something that's not a KP1, or do you?
Well, you don't get this thing. So, but yeah. So typically, so you get something. It's not this thing, and the issue of what. So there was something which. Yeah, so I guess. So what do I say here? I think it's not a K-pi1, but there's something closely related to it, which is where you, or at least in cases you can, you need to put some additional like signature condition and blah, 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 like some conditions on like a CM structure. But so also it tends out to be the case that it tends to be the case that you usually can't get all the way to the rational numbers when you construct things which are K-pi1s. But yeah, I guess there's an interesting question of where the gap is. But basically, let me say, when you take arithmetic groups, the generalization of this B gamma presentation, which I wrote, was a locally symmetric space. For gamma. And so that's a K-pi1. It typically is not going to have any algebraic structure. So we need this thing to have algebraic structure. So we need to be in the Shimura variety case.
So you're saying it's going to be some kind of stack in, say, analytic spaces or whatever that does not come from an algebraic stack, the natural thing to define?
I think there will be an algebraic stack, but it just won't be kind of this type of thing. So yeah, I guess it won't be a K-pi1 for an arithmetic group.
I have a related question, Tony. So how do you parse this equality? So the top thing is a homotopy type, the bottom thing is a stack. So what does it mean for them to be equal?
Well, a stack has a homotopy type. It's
Okay,
the-
so you take the étal homotopy type of that stack.
Yes.
Well, even the Betty homotopy type actually, sure.
Sure, sure.
We
But
could
it's
take
not the case that you can write BSP as the functor of points of some stack, right? That's not going to be correct. Right?
BS.
Yeah, BSP blank is not equivalent to the moduli stack of Abelian variety.
Oh, you're saying, is this like so there's this
BSP2G is a stack. Yes,
I see what you're saying. There's also a stack called this. That's what you're saying, right?
There is a stack called BSP2G.
Yeah, there's a stack called BSP2G, exactly.
There is this stack as well, but yeah, so it's definitely not this thing, and it's also not this thing, but right. So what maybe I should just say what this means is this is the homotopy type of.
Yeah, I understand. Okay, cool.
But what I want to say it's not equal, but oh, sorry, when totally real, yeah, it's okay.
Cool.
Okay, so maybe we should thank Tony again for the talk, and